So as Avi mentioned, the main focus of my work is exoplanet atmosphere characterization from afar. And so the astronomers in the audience who know me keep coming to me and saying, why are you talking about the solar system? That's not what you do. But I actually think I'm the perfect person to be talking about this because I'm so keenly aware of the limitations of studying these planets from far away. And so I am the #1 cheerleader for seeing them from close up to learn as much as we can about their habitability. And so I thought I would just do a little bit of a historical retrospective about what we've learned from flybys in the solar system. And the first flyby was in 1962. It was Mariner 2's passage within 40,000 kilometers of Venus. And this is a figure from a review paper about the flyby. And there are a couple things that I just love about this figure. So, well, okay, first of all, the review was published in Space Science Reviews Volume 2. It's because space science didn't really exist prior to Sputnik in 1957. And the other thing is that the labels on this figure, I think, might be written by hand or stenciled in by hand. And I just think that's a fascinating juxtaposition of the difference in technology between 1962 and now. So this was, they were writing their figure labels by hand and still were able to do a flyby of another planet. So Mariner 2 had a very fraught voyage to Venus. In fact, it was thought that the mission might fail because one of its solar panels short-circuited on its way there. But fortunately, as it got closer to the sun, there was more solar power available for the remaining panel, and so it was able to transmit information back. And Mariner 2 had a whole suite of instrumentation. Some of it was focused on studying Venus. Other instruments were focused on studying the interplanetary medium. And I thought I would just highlight two that I found especially relevant in the context of Starshot. One of them is that Mariner 2 had a microwave radiometer. This was an exceptionally simple instrument. I think it had just 3 channels operating in the microwave. And what the microwave radiometer allowed Mariner to do was map the surface temperature of Venus. And this was the first robust evidence that there was strong greenhouse warming in the atmosphere. And so a question, of course, is could we measure the surface temperature of a planet like Proxima? And I wrote a little paper with Avi right around the time of the discovery about prospects for using planned facilities to observe the climate of Proxima b. And so the idea we had was that so the planet we expect is tidally locked, so it's hot on the day side and cold on the night side. And depending on how much atmosphere it has, that controls how much energy can be redistributed around to the night side. So here are extraordinarily simple climate models for what the temperature might be like as a function of how much energy is redistributed. And we found that it's potentially possible with JWST to observe a thermal phase curve of the planet over its full 11-day orbital period and measure the temperature contrast from the day side to the night side. But of course, that only gives you a hemisphere average view of the planet's temperature. And ideally, what we would love to have is a map of the entire climate of the planet. And so something like a flyby mission would ideally make that happen. A second instrument on Mariner 2 was a magnetometer. And it found that there was no sign of a magnetic field from Venus. Indeed, Venus has a very low magnetic field strength. And we would love to know, in the case of Proxima b, whether that planet possesses a magnetic field as well. This is something that can't be observed remotely. And the reason it's especially important for Proxima b is that while in many senses the planet appears to be an Earth twin, so comparable temperature, similar mass to the Earth, its orbital period is much, much shorter, which can cause because it's tidally locked, the rotation rate is slow, and that can shut down the magnetic dynamo in the core. And so it's possible that it lost its magnetic field, which could have drastic implications for its atmosphere, right? So if you don't have a magnetic field protecting you from the flares from the star, the stellar wind, that can lead to atmospheric escape and erosion. Okay, so I want to switch gears from Mariner 2 and talk a little bit about the New Horizons mission to Pluto, which is, fast forwarding 50 years in the future. This now represents the state of the art in planetary flybys. Oh, I should have said, Mariner 2 did not have a camera. I think at that time it was so difficult to make a functioning camera in the environment of space that they just said, this is too hard, we'll do it later. And indeed, that's what happened. The imaging technology and spectroscopy for New Horizons was absolutely stunning. So this is one of my favorite before and after shots that I've ever seen. So on the left, there's the best Hubble image of Pluto taken prior to the flyby by New Horizons. And on the right, you can see the exquisite spatial resolution that we got from New Horizons. And if you zoom in, here's a view of the surface just as New Horizons passed by. And you can see remarkable geologic features. So there are mountains on the surface of Pluto. These are roughly 2 miles in height, we think, so comparable to Mount Fuji in Japan. And this is indicative of perhaps cryovolcanism, so analogous to volcanism on the Earth, but rather than having magma, you have volatiles like water. And we would love to know whether a planet like Proxima b has tectonic activity. Because on the Earth, plate tectonics are responsible for the carbon silicate cycle. So you have planets, or you have volcanoes outgassing CO2, which then weathers rock, and the CO2 is reabsorbed into the mantle of the Earth, and this creates a stabilizing feedback for a clement climate on Earth. And so it would be fantastic to fly by Proxima b and find out whether the planet has anything analogous to that. Okay, so another really transformative result from New Horizons was spectroscopy, not just imaging. So this is the UV transmission spectrum of the planet's atmosphere, and you can see, so there's a model on the left and the data on the right, and you can see features from various important atmospheric components. So there's nitrogen, there's methane. You can also see photochemical byproducts, so C2H2, C2H4, which are produced by photolysis of methane. And we've heard a lot of discussion about how interaction with UV flux for planets orbiting M-dwarfs can lead to false positive biosignatures. For example, if you lose a lot of your water, you can be left with remnant oxygen, which we could interpret as a biosignature. So it would be fantastic to get a really high quality spectrum for a planet like Proxima b. And one thing that I've learned from my work on exoplanets is that the more spectral resolution you have and the wider the spectral range you have, the more you can learn about the overall composition of the planet's atmosphere. So it's very difficult to interpret what you're seeing if you measure a single molecule in isolation. Okay, the last thing I want to talk about is, this is cheating a little bit. It's not technically a flyby, but this was Cassini's recent dive into the plume around Enceladus. So Enceladus is a very small moon of Saturn, and it has a subsurface ocean that is, the heat source for that is tidal heating from Saturn and Saturn's other moons. And the ocean erupts in these geysers that you can actually see. This is a picture of them taken by Cassini. And so Cassini is nearing the end of its lifetime. And the ultimate plan is to crash it into the surface of Saturn so that it doesn't accidentally impact the rings or one of the other moons. And so they're embarking on riskier and riskier trajectories for the spacecraft. And a recent one was to dive through one of these plumes. And there's a mass spectrometer on board Cassini. And what it was able to measure, so basically what happens is it dives through this plume and it engulfs some of the particles that are in the spray. And they are ionized and then pass through a magnetic field. And the lighter the particle is, the more easily it's deflected. And so you can get a spectrum, a mass spectrum, that tells you what the composition of the incoming particles is. And what they found in this plume is that there's a lot of molecular hydrogen. And this was very puzzling at first because you would expect hydrogen to escape from something that has such low surface gravity. And the leading explanation for why the hydrogen is there is that it's produced in the same way that you get hydrogen around geothermal vents at the bottom of Earth's ocean. So as you have hot water pouring over rock, the rock can be oxidized, so you take away the oxygen atoms and you're left with this remnant hydrogen. And this is tremendously exciting from the prospect of habitability for Enceladus, because molecular hydrogen is a great energy source. There's a lot of energy stored between, so it's easy to snap that bond between the two hydrogen atoms. And that provides a great energy source for microbes that might be lurking at the bottom of the ocean there. And, all right, so I want to end with some caveats. So it's worth noting that as exciting as these flybys are, all of the cases in the solar system, the spacecraft was passing within order of magnitude 10,000 kilometers of the planet or the moon. And currently, we don't actually know the position of Alpha or Proxima Centauri well enough to be, even if we had a perfect trajectory in the launch, we still don't even know the position of the stars well enough to aim this close. And in addition to that, the payload for these instruments is tens of kilograms. So these are very heavy things that are being sent. And so clearly, if we wanted to equip Starshot with something analogous to this, it would have to be in a very different form. That said, I would say that the main lesson learned from flybys in the solar system is that every time we get so close to another body, what we learn about it is absolutely transformative for our understanding about what it's like. And so I think Proxima B is, while this is an extraordinary challenge, it's also an extraordinary opportunity. And so that's why I'm excited about Starshot. I thank you. I'll take questions.
Yes. Okay, go ahead.
Nice talk, Laura.
Thanks.
Just a comment, or maybe a question to you about this last point you raised about needing very high accuracy for sending a probe to Alpha Centauri. We could imagine sending like a spray of craft, because we get more than one shot, right? So
right.
Even though we don't have basically to hit it right the first time. So I wonder if you've any ideas about that as well.
No, that's a great point. Yeah, and the thing that gives me hope about this is that they're sort of like disposable items. You can just send them out, a whole fleet. And hopefully, eventually, some of them pass by close. And also the fact that the planet is orbiting on such a short time scale means that if you have multiple spacecraft going by, you see different angles of the planet at different times.
There was another question in front of Blake's. Yeah.
Hi, Laura. Jim Casting, Penn State. The Enceladus flyby is really exciting, and the authors of the paper that you mentioned derived a free energy change from the hydrogen and methane and CO2, and they get about 80 kilojoules per mole, which is a very large amount. So my question to you is that make it more or less likely that there's life under there?
That's a great question. I mean, so one comment about that result is that given that there's so much energy available, if there were some life down there, it surely would have gobbled all of it up. I remain agnostic at this point.
Phil?
So actually, there is onboard propulsion that does have slight lateral translational possibilities.
Mm-hmm.
It's of order 1 to tens of AU, depending on the ISP of the thrusters. So you might want to take a look at that. But my question was, have you looked at the range or the optimal range of spectroscopy and the angular resolution, as was discussed in the previous talk, that would be reasonable in order to achieve some of the goals? So previous talk mentioned that having spectroscopy over the surface would be great, which I agree. But we would like to understand to what extent would the spatial resolution impact the knowledge that we would get from that, and over what range would we like spectroscopy?
Yeah, that's an excellent question. I would say that, given that most of my work is on using HST and soon to be JWST to study these planets from very far away, we're taking a completely unresolved point source and inferring hopefully a tremendous amount about their atmospheres. So even if you don't have any spatial resolution whatsoever, you can still learn a lot. And I would say the more resolution, the better. As for the second question of what the optimal resolution is, it depends, of course, on what the atmosphere is made out of, if it exists at all. And that's something we don't know. And so I would say the near-infrared is very interesting because there's a lot of strong molecular absorption features there. So 1 to 5 microns is really the sweet spot, if you can get it. 1 to 2.5.